Welcome back to the deep dive. Today we're going to get into something really interesting: advanced signal transport.
Yeah, we're looking at how massive satellite TV systems, I mean, the ones that run hotels or even whole communities, get around the problem of distance.
And they do it using, well, pure light.
Exactly. We're looking at a piece of gear, the Thor Broadcast optical transmitter, that really showcases this. It's a box designed to handle up to 6 L-band RF channels.
And for anyone listening, L-band is just the standard frequency for satellite signals. We're talking DirecTV, Dish Network, that kind of thing.
Right. And the problem this all solves is, a classic one.
Scale and distance.
Scale and distance.
Yeah.
If you've got a big satellite disher array, you've got maybe 4, 5, 6 thick coaxial cables.
Heavy, bulky stuff.
And you have to run them maybe hundreds of feet back to your equipment room, your head end. Every foot of that copper cable just eats away at the signal.
So your picture quality is always at risk. It's a constant headache.
It is. And that's why this is such a game changer. It takes all those messy electrical feeds and puts them on a single strand of fiber optic cable.
And the promise there is basically infinite distance with what, 0 signal loss?
For all practical purposes, yeah, 0 sacrifice in quality.
Okay, let's unpack that. How do you cram 6 separate independent signals down one tiny hair-thin piece of glass without them all just crashing into each other?
That's the beautiful part. It's the whole engineering leap here. It's a technology called coarse wavelength division multiplexing, CWDM.
That's a mouthful.
It is. But the idea is simple. Instead of pushing electricity, you convert it. The box has these powerful internal lasers.
Lasers, okay.
And each laser takes one of those L-band signals and assigns it a totally unique frequency of light, a different color.
Oh, I see.
Then an optical multiplexer inside combines them all. It's literally a rainbow highway for all your TV channels.
Wait, so you're telling me we've gone from like miles of heavy copper that needs constant boosting and maintenance to a single piece of glass carrying different colors? That has to fundamentally change the cost of installing a system in a large building.
Oh, absolutely. And it's built for that.
Yeah.
You can take the 4 standard feeds from your satellite dish, and you'll still have room for, say, 1 or 2 local over-the-air channels.
Your ATSC signal.
Your ATSC signals, exactly. And you ship all 6 of them together, perfectly discrete, on one fiber.
So once you have this rainbow of signals on the one fiber, what's next? I mean, how does that one little strand feed dozens of hotel rooms?
That's where the distribution power comes in.
Yeah.
That single optical signal can be split. You can split it and amplify it to feed up to 32 separate endpoints.
32 from one transmitter.
From one box, yeah. It's perfect for what they call an MDU, a multi-dwelling unit, or a hotel.
Yeah.
It's almost plug and play at that scale.
Okay, that tech is cool, but complicated tech can mean a complicated setup. What about the installer on the ground? Is this easy to work with?
It seems like they really designed it for that. It's not just a passive box. It actually has a microcontroller inside, and the chassis is temperature controlled to keep everything stable.
So it's managing itself.
It is. And it handles the really critical stuff, like providing power to the LNB on the dish and managing the polarity locking tones. Those are the things that ensure you have a solid, consistent lock on the satellite.
And I saw it has an LCD display right on the front, which is nice. It shows the RF input levels and the final optical power.
Which means the installer doesn't have to break out, expensive test gear just to see if it's working right. They can just look at the screen.
A huge time saver. So what does this all really mean then?
I mean, it means the entire physical backbone of how we distribute video is just different now.
Right. We've moved beyond the old limits of copper cable by translating those electrical signals into, well, colors of light to send them over huge distances on fiber.
And if you think about the bigger picture, this whole idea of wavelength multiplexing, packing different feeds into one strand using colors, is the key to everything scalable in the future.
Which leaves you with a really interesting thought to explore.
Yeah, it raises a big question. If a single fiber today can reliably carry 6 HD signals, what's stopping it from carrying 600 or 6,000? What is the actual physical limit of how much information we can send down a single strand of glass?